Hello everyone, welcome back to the next topic of today's CS61C lecture, where I discuss different recommended methods to actually translate between different number bases and some other techniques that I think are generally useful that you should find useful as well. So the first thing I recommend is actually a method of how you translate between different number bases. For example, if I want to translate from hex, I recommend that you really only translate hex to binary. And also, I recommend that you translate binary to decimal. While it is possible to go from decimal to hex or hex to decimal, I'd kind of advise not to do that because that just gets a little bit more complicated. I mean, if you have a computer with you, you can quickly just plug in some numbers, or if you're just a math whiz, sure, you can do that as well. But for most people, they find it easiest if they go from binary or hex to binary to decimal, for reasons that I will show later on in this video. So some other things that I recommend you actually put to heart is the powers of 2. So 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7, 2 to the 8, 2 to the 9, and 2 to the 10. So 2 to the 0 is 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. I really recommend that you guys actually remember these because it will just make your life so much easier. I mean, slowly you'll get into the habit where I know 2 to the 5 is in the very middle, and 32 is a very common number, so 2 to the 5 is 32. Maybe I have 2 to the 4, so I know it's the thing that's right before 32, so half of 32 is 16. So you can use those type of tricks if that helps you at all. But in general, you'll find that you will get to know this table very, very well as you actually continue to work with these numbers very often. Some other important things you should probably remember is 2 to the 10 is a kibbe, 2 to the 20 is a mebbe, 2 to the 30 is a gibbe, 2 to the 40 is a tebbe, 2 to the 50 is a pebbe, 2 to the 60 is an XB, 2 to the 70 is a zebby, 2 to the 80 is a yobby. Typically, we won't be really using things that are this high, but it is still good to know these. It is also on your green sheet, so you will have a reference to this on for exams or just in general life. I mean, exams are kind of weird now because we're all online, but you'll get used to everything. And some other really useful things that you should know with this is, like, say I have the number, or the value 2 to the 12. Well, if I want to represent this with, like, these names and some other information, I can quickly convert this down to 2 to the 2 times 2 to the 10. And so this 2 to the 10 is a kibbe, and then 2 to the 2 is 4. So I have 4 kibbe, so that's what 2 to the 12 is. Just like if I had 8 gibbe, I know that 8 is 2 to the 3, and I know a gibbe is 2 to the 30, that's what I have up here. So this is this, so if I multiply these two together, this is 2 to the 33. So those are some tricks for doing those type of conversions. Now let me start converting between different bases. So let's say you want to go from a larger base to a smaller base, or a smaller base to a larger base. So let's say I want to go from base 2 to base 10. So I can have the value 0 be 1, 0, 0, 1. And I want to translate this to base 10. So the thing that I was talking about in previous lecture videos is that I can just represent all of these as powers of 2. So this is 2 to the 0. This one right here is 2 to the 1, 2 to the 2, and 2 to the 3. Then I just multiply these two together. Because this is a 1, I'm going to keep it. This is a 0, this next place right here is a 0, so I'm not going to keep it. So this is going to now just be 0. This one is going to also be 0 because we have a 0 in this place. And finally, 2 to the 3, we're going to keep that because we have a 1 in that place. So what I've just done is I've just said I want to keep 2 to the 3 and 2 to the 0, which means I want to keep 8, and I want to keep 1, which means that I've got a value of 9 right here. Now let's say I want to go from a larger base to a smaller base. Well, it's a little bit more complicated, but I'm going to show you one of the general tricks that you can use for this. So say I want to go from base 10 to base 2. And I want to use the number 14. Why not? Well, if I have this, if I have a base that I can't quickly just see, oh, 14 is equal to this or this, then I'm going to have to start doing a few more complicated things. So the most basic thing you can do is figure it out by division. So I can take the base here and keep on dividing out the base so then I can get each essentially bit or digit, depending on what the actual base you are converting to, in this sequence, such that this is the least significant digit, so least significant bit in our case here, and then on the right side it's the most significant bit. So let me start dividing this out. So 2 goes into 14 7 times, and I have a 0 remainder. Now I take this here and I put it in here, so I'm now dividing out what I just divided from. And I'm going to now do this, which is 3, and I have a remainder of 1. Now 2 goes into 3 one time, I have a remainder of 1, and finally, let me move this over, 2 to the 1, I can't put that in there at all, but now I have a 0 here, which means that I'm done with all my division, but I couldn't put that in there, so I have a 1 there. Here's my most significant bit. So in this case, you start to read the number like this. So the number that I actually got was 0b 1 1 1 0. So this is the number in binary for 14. You can do some quick math to check this. This is the power here is 1, but we don't use it. 2, 4, 8. And if you add all this together, this is equal to 14 base 10, which is exactly what we wanted. Another trick that you can use is, say you know this number is really close to something that you know the power of 2. For example, I know that this number is close to 16. It's just different by 2. So if I know what 16 is, which is 0b 1 0 0 0 0, I just need to subtract 2 from this number, which means I can do this by just subtracting 2, so 0b, so basically minus 0b 1 or 1 0 like this. And then I can just kind of do subtraction. Subtraction is a little bit weird with this because technically you'd be using like 2's complement or something like that, but I kind of do this like normal addition kind of thing just because it just makes life a little bit easier. So I can't take anything, or 0 is here. I need to carry out of here, so this turns into a 0. This is 2, but I can't here, so 2, so this is 1. So now I have 2 here, so 2 minus 1 is 1, and then 1, and then 1, and then this is 0. So I just got that this is equal to 14. So this is a little bit of a kind of hackish when you're doing some quick math for these type of problems. Technically what you can do is you could convert this value into a 2's complement value. So I could turn this into -2, and then it would be really easy to just add those two numbers together. But this is kind of I'm really lazy and I'm just going to subtract numbers how I would normally subtract things. So now let me actually talk about another technique that you should have. Let's convert from binary to hex. So let's go from binary to hex. So let's say I have a number 0b1001 1000 1111 0011. You might have noticed that when I was kind of saying this number, I was actually kind of pausing in between each value that I was saying, or every 4 basically bits that I was saying. The reason for this is if I start to group this hex value into groups of 4, I've now figured out how I need to convert each little section of the bits into a hex nibble. Because once again, hex is base 16, binary is base 2. That means I can fit 4 bits inside one hex nibble. And that's what I've just done here. I've just split this up into 4 hex nibbles, which means the value here that I'm going to get, so this is 9, because 8 and 1. This is 8. This is all 1s, so I know this is F, because that's the largest possible binary value, so I know it has to be the largest nibble, which is F. And then 3, because this is 2 and 1, so this is 3. So my hex value that I got is 0x98F3. Say I wanted to go from hex to binary. So say I had the value 0x, let's do something easy, 2, 1, 3. So once again, I just need to split this up into the different nibbles that I have. So I know 2, it has to be 4 bits essentially. So I'm going to have 0b. So 2 represented with 4 bits is just 0, 0, 1, 0, because this is 2 to the 1, 2 to the 2. The next value is 1, so 0, 0, 0, 1. And finally 3 is 0, 0, 1, 1. So that is a quick conversion from hex to binary. So let's say you want to go from maybe binary to base 4, for example. How would you actually accomplish this? Well, let's do, so this is base 2 to base 4. So let's say I have the value 0b, 1, 1, 1, 1, 0, 0, 1, 0, 0, 1. Sure, that should be fine. So similar to hex, I can actually group this into smaller sections. Like I can say this is one base 4 thing, this is another base 4 thing, this is another base 4 thing, this is another base 4 thing, and this is another base 4 thing. And so if I start to convert these, once again, base 4, I can only have values 0, 1, 2, and 3. So this would make sense because I can only represent with 2 bits up to 3 possible, or up to 4 possible values where we have the largest possible thing being 3. So in this case, I have 1. Here I have 2, 0, this is 3, and this is 3. So this value in base 4 is 3, 3, 0, 2, 1. So this is base 4. How about base 8? Well, I can use the exact same trick here, and let's actually copy this number right here, so then I can do the same number here and show you that, once again, numbers are just how you interpret them. So it's up to you how you do this. So base 8 is, base 8, so 2 to 8. Base 8 is very similar to the base 4 conversion, but instead I'm going to be grouping this into groups of 3, because now I have 8 possible values from 0 to 7 that I can represent. So this, and technically this one is up here, and I have 2 imaginary 0 padded numbers here, but I'll get into that in a second. So this one, it's just 1 like usual. This one's also 1. This one is all 1s, which I know is 7 because that's the largest possible value that I have with just 3 bits. So, but if you really didn't realize that, you can see that this is 4 plus 2 plus 1, which is 7. So this is 7. And then finally, this top section here, I think they're called octals for base 8. This octal right here, we only have 1 bit here, which means that we have to just 0 extend, or basically sign extend that value out here, so then, or 0 extend really, that value out here, so that you're able to actually represent this. So in this case, its octal value is just a 1. The reason why I was kind of talking about sign extension, you shouldn't do sign extension for this. The whole reason why I was even saying that was because, say this was a signed number. With octal, you would still, if you only had this many bits, so in this case I have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this case I only have 10 bits. I wouldn't want to add extra bits, and technically those bits wouldn't matter, but I mean, it's up to your interpretation of what those bits really mean. In this case, we only have 10 bits to represent some value, so that's what I have here. And so then I have this really clear 7, 1, 1 in base 8, so that's what this value is. So those are some of the different tricks that I have for converting between like the different bases that I'd recommend you actually really know really well, because they'll be very helpful for you. But that's not the only trick I have in my book. So let's start to do some very quick binary binary conversions. So what if I have the number 31? Well, does 31 look like some other number that I showed you recently? Where is it? It's somewhere here. Doesn't it look like some number that I told you about recently? If you were pointing to 32, you're right. It is. But what is this? So this is equal to 32 minus 1. Well, do I know what 32 is? Well, yes, it's 0, B, 1, and then 4 zeros. Because remember, 16, 8, 4, 2, 1. There we go. 5, wait, hold on. 0, 2, 1, 2, 3, 4, 5. Yeah, okay, there we go. I missed a 0. But yeah. Yes, you can quickly just do that. I know all the binary stuff really quickly, so that's easy. But I make math errors sometimes, so you should always double check your work, guys. So this is 32. So 31 is just 1 less than that, which means that I know that it has to be all 1s down here, and then a 0 up top here. So this is what the value of 31 is. And if the way how you can think about this is, this bit is 32, and it's all the other bits added together have to be 1 less than that, because that bit is that value. What about if I had 33? Well, I can use the same technique, and I know that has to be 1 more than 32, so 0b1000001, because I just added 1 to what the value of 32 is. So these are some very quick techniques that you can use to actually convert between binary and decimal values if you know a number that is very close. And it can be very useful, like say I give you the number 53, and I ask you, what is the number 56 in binary? And I give you the number 53 in binary, that is. You should be able to go quickly from the value of 53 to 56, or whatever I said before. So you should get familiar with being able to quickly do some conversions by some basic math tricks. It'll just help speed up your conversions really quickly. And I just recommend it, because slowly you'll be using it a lot more in this class, and you'll just find it really useful to be able to quickly just get those things kind of done. So the next thing I kind of want to talk about today is bias notation, and 2's complement, and some just tricks for doing addition and that kind of stuff. So for bias notation, so the way how bias notation works is I take an unsigned value, and then I add some bias to it. And then this will give me my actual bias, my actual value. Just a little side note, some people say you add the bias, some people say you subtract the bias. As long as you're consistent with it, and typically we will try to always say it's adding the bias, but we'll always typically say if we add or subtract the bias. I like to say it's added because theoretically the bias is the thing that is negative, and that's the thing that's really changing it, and you're just adding some unsigned value to the new value that you want. So that's just a little side note that I thought you guys should know. So if you see materials like that, they can go back and forth between if it's a plus or a minus. But let me actually go through this. So the unsigned value is like, say I had 3 bits, I can only represent values from 0 to 7. And so this value here, so let's just say I have a value 0b101. So my unsigned value of this is what? Well, it is 4 plus 1, which is 5. Now let's say I gave you a bias of -5, why not? So I could give you a bias of whatever, because that's the nice thing about bias notation. Essentially, I am shifting the same exact range of bits up and down based off of whatever my bias is. But the distance between each bit, or each bit, or place essentially, is the exact same amount. So it's not like I can make it so that I have a much larger range with the same number of bits. The range stays the same. It's just the location numbers that I can represent could be anywhere. So that's a very important thing to realize with bias, which is really helpful. So in this case, I'm going to add this unsigned value to the bias value, which in my case is -5. And so I'm going to get that this value in bias notation, the actual value that I'm trying to represent, is 0. So this is how you basically convert the actual unsigned bit representation of your value to your actual value from the bias. This unsigned information, or this unsigned representation, is very important to understand as well, because that is really how it is represented inside of your hardware. We just have some unsigned bits, and we're just mapping numbers to this. Even 2's complement technically is like that. We just have n bits, and we're just mapping different values to each of these bits. The way how we map them just gives us a little bit of benefits for like doing a quick addition and that kind of stuff without any really extra bad hacks. But speaking of 2's complement, let me actually get into some 2's complement. So there's two different ways how to look at 2's complement. The base representation of it is 0, like say I have a number 0, be 1, 1, 1, 0, and so I only have 4 bits. So the first way to look at it is my largest bit is negative and all the other bits are positive. So in this case, I have 2 to the 0, which I don't really have because I have a 0 there. Then I have 2 to the 1, 2 to the 2, and 2 to the 3. But 2 to the 3 is our largest bit, so that's a negative bit. So what I'm doing here is I'm doing 2 to the 2 plus 2 to the 1 minus 2 to the 3. And so this is 4 plus 2 minus 8. And so for this value, I get negative 2. So that's the whole idea with 2's complement. It's just the only bit that is different is the most significant bit. That is the reason why we can use it as a sign bit, because if that is set, then we know the number has to be negative. And the other trick to this is we know that we cannot have a negative value, or we cannot have a value that is positive or 0 when the most significant bit is set, because, as I said before, if that bit is set, that means all the bits behind it, if those were all added up, at most I'd get 1 minus that value. And that's actually a really nice trick to know, because what this tells us is that if I have negative 1, for any amount of bits, that means all bits are set. For example, this number that I gave here in 4 bits, that gave us negative 2 with every bit but 0 set. If I included that 0 bit, then I would actually get negative 1. So this is a really nice trick because it allows you to set all the bits of a number with just one single operation. I just set the value to negative 1. And you'll find that this will be useful when you start to do some bit arithmetic and such, and bit operations in your C programming. So the other trick for 2's complement is flipping the bits and adding 1. So I'm going to use the same exact number to show you that these are 2 of the exact same ways of doing the same thing. So I'm going to do 0B1, 1, 1, 0. So first I'm going to flip it, then I'm going to bop it, no, I'm just kidding. So first I'm going to flip it, 0B, 0, 0, 0, 1, and then finally I am going to, here, let me turn off my volume so then you guys don't hear my Mac. So then I'm going to add 1. So addition is just similar, so I have 1 plus 1 is 0 here, carry it out, 1 plus 0 is 1, and then 0, 0. 0 be this. So this value is equal to 2, but I had to flip the bits and add 1, which means this is actually negative 2. And these are the exact same values as we can see here. So these are the exact, or these are two of the same ways of actually doing convergence. The reason why I bring this up is because you might notice in different C programs, they sometimes flip the bits, like negate, do the little tilde. It's a bit operation, you flip the bits. You'll learn this a little bit more later on, especially in one of the labs. They might flip the bits and then add 1. What that is really doing is it's negating that value. So it's just another way of doing it. Okay, so the final thing I kind of want to get into is unsigned and 2's complement addition. And technically it's also the subtraction, but, you know. Wait, is that 2 T's? I don't remember. I'm sorry. I misspell everything. You'll notice some of my Piazza posts, I'll misspell some word or mistype something. Yeah, I'm sorry about that, guys, but whatever. Okay, so let's try to add some numbers together. Let's add 0B 1 1 0 1 1 with 0B 0 1 0 1 1. So technically, doing this addition for 2's complement and unsigned is the exact same thing. It's just how you interpret the values is different. So if I start adding these, the least significant bit, so this is 1 plus 1 is 2, so I have a 0 here because, once again, as I said in the previous lecture, if I have 2, I have to carry this to the next place. Now I have 1, 2, 3, 3. That's even higher than 2. Well, what do I do here? Well, in this case, I plop a bit down, so now I have 2 bits, and that means that I have to carry that next bit over. Because remember, 2 is technically the next place. It's just like when you get 10 in decimal, you're in the tens place now instead of the ones place. So basically that's the exact same method here, so we carry that over. Next, we just add a 1 to this one, because we have this carry bit. 1 plus 1 is 2 once again, so that's a 0. And then we have a 1 here, and then 1 plus 1 is 2, so that's 0. And then we have a carry out of 1. So I said that this is a carry out and not an overflow, because depending on how we're actually representing this value, it actually may not be an overflow. For example, if I have if I'm interpreting this as an unsigned value, wow, I cannot write, sorry guys. This is an overflow. So basically, if you have an unsigned value and you ever have a carry out that is a 1, that means you've overflowed. For example, this number right here, this top number here in unsigned is actually 27. This bottom number here is 12. You can do the math, I already did it. And this is equal to 39. But this value is actually equal to 6, so these two are not equal to each other. That's why I overflowed. That's why I'm saying I overflowed this value. It's because that is arithmetically not the correct representation of this with the number of bits that I gave. If I had an extra bit, then I wouldn't have overflowed. But that's the important thing. If I have a limited set of bits, I might not be able to represent the new value that I just created. Now let's look at 2's complement. Wow, toes. 2's. Okay, so this one is actually good. And I can do this just by eyeballing it without even bothering to look. But let me just go through this so then you guys see this too. So 2's. So this top value here, I know it's negative because the most significant bit is set. So what I'm adding together is -5. You can do this quick addition here. And then this is 8, 9, 10, 11. And so this is 11. So then this would be equal to, what is this value? So this is 6. Wait, is this 6? Yes, it is 6. Because this value is also 6, which is the same exact thing, which means 2's complement is good. Sorry, quick math, I know, sometimes not always the fastest with that. But you can see 2's complement actually did not overflow. But I had already told you that it did not overflow, and it wasn't that I had already written that down or figured this out myself earlier. It's that I realized that for 2's complement, overflowing, you can overflow. Oops. Let me rewrite this then, it's cleaner. So there's only certain times when you can overflow and you cannot overflow. So let me just do these two things. So we're going to be adding different values together, and let me just change the color so it's really clear for you guys. That's a nice color. So the values that can overflow with 2's complement is if I add a positive and a negative number. Or sorry, a positive and a positive number, or a negative and a negative number. Just like I cannot overflow if I add a positive and a negative number, or a negative and a positive number. You can do the quick math of this, but you'll realize that you cannot ever overflow with these possible things, and you can always overflow with this. So the quick check, if we ever have a question of, does this number overflow, is this most significant bit here or here set? If one of them is set and the other is not, that means we will never overflow. If both of them are set to 1 or both of them are set to 0, then we have a chance that it will overflow, and you'll actually have to determine based off of our carry-out bit. So if we are adding a positive and a positive, or a negative and a negative number, if we have a carry-out bit, then we need to check to see, was it a positive and a positive number that we're adding together, or a negative and a negative number that we were adding together. Based off of that, we'll be able to determine if we've actually overflowed. So those are some of the different tricks that I have for conversions and simple addition and that kind of stuff. I hope this actually will help you when you're actually starting to work on doing some basic conversions. I really recommend that you guys spend the time and actually do the practice homeworks, or do all the practices that are on the homeworks as well, and try to actually do it by hand instead of just doing it by computer, because the faster you're able to do it by hand, the faster you'll be able to really think about all these problems. And it'll just make your life a lot easier in general. It's not just for an exam, it's because if you start to really do C programming or that kind of stuff, you're going to have to be doing a lot of arithmetic, or you're going to be having to do a lot of checking a number. Like, I might get a hex value, I need to quickly convert that to see which bits are set, because I might be using a, like, integer, which is 32 bits or so, as, like, a settings field, where if this bit is set, I want to do this, if this bit is set, I want to do this. So if you get to know these techniques very well, you'll be able to do a lot of these conversions very quickly. Well, I hope this video helped, because it was also a newer one.